Yeah, where's that going to go? Okay, I'll put it on the floor. If you see me suddenly reach down to the floor.
Okay.
I'm going to talk about a little bit of the history of the ram, and taking us from the first recorded instances all the way to the 21st century. So we'll talk about first the genesis of this project, which all of you can see in the back, and I hope you'll have a chance to visit the posters and see the model. And that was to understand what preceded the ram as a weapon. This part of the ship, what we call in the cutwater, how and why that may have developed and perhaps evolved into the ram. So you notice a lot of speculative terms there, and I'll explain why. I'll talk a little bit about the cutwater study, take you through to the ram as not but the primary naval weapon of the 19th century, and a little bit about the bulbous bow, which we know and love today. I don't know how we were supposed to run this, but here's the way normally we have X number of minutes for talk and then questions. What I'm going to suggest is if there's any clarifying questions that you want to ask while I'm talking, please feel free. Now, it's kind of dark, so it's a little hard to see. But if you raise your hand, I'll be able to see. I suggest you don't understand something, there's something I misspoke, raise your hand, I'll try to find you. But I'd rather save the sort of the expanded questions until the end. Okay, so we're starting with the trireme. Now, you saw the picture that John had at the very beginning of the current full-scale attempt at a replica. That's the Olympias, which is now in Athens. It's out of the water. Here's the drawing that was made back in the 1980s by a British naval British constructor, John Coates. And the ram as a weapon, there we are, is pretty well known. Bronze, heavy, has 3 fins that are intended to penetrate an enemy hull, disable it. One of the questions was, why did this develop and how? Because the earliest depictions and not just depictions, representations and discussions of the ram as a weapon used in battle only date to about 540 BCE, thereabouts. However, there are artistic representations, iconography that show things that look like rams, but aren't rams, well before that heavy bronze structure that we know existed circa 540 BCE. Depictions as far back as 1000 BC, actual sites that have been uncovered in different places. You can see probably most clearly here and here, 2 pointed bows. And what we can understand from both this kind of archaeological evidence as well as these depictions is these are not weapons. The structure is far too light for deliberate, intended, systematic ramming as a part of a major set-piece battle. So the question becomes, why were these kinds of pointed bows developed in the first place? And in the literature, you often see ideas floated about what it could have been. One of the things that we wanted to investigate was, did this, we'll call cutwater, provide anything like a benefit to the sailing or rowing capability of these vessels long before they became weapons? And by extension, did that somehow evolve into the weapon that we now know and understand today? So that was the question we were trying to ask. did the cutwater provide, to use the terms that the people here at Davidson Laboratory use, any hydrodynamic benefit? So the way we structured the study was to build a model, and the model, as I mentioned, is in the back. And because the Davidson Laboratory had a very capable numerical cutting machine, it was a fairly straightforward process to first, create the model. Sometimes the laser works, sometimes it doesn't. Okay. Well, it's a hands-free device. So the first idea was to create the model with a flat piece that we could put different bows on. So the whole model without a bow was first carved. First, a bow that would represent something that, let's say, a merchant vessel of the time, rounded stem would look like, would be attached and tested to see what a more conventional ship would do under normal rowing or sailing conditions. Next, and it's a little hard to see here, but it's a cutwater that you'll see over there, is a long pointed segment would be used, and then we would compare that with the trireme, which had been model tested in Athens some years ago, which had a ram bow. So the idea, as to summarize, was compare the regular bow with the cutwater bow. That's what we did here at Stevens, and then look at the results that were generated in Athens back in the 1980s and see how those compare. Here's the model that was tested at the National Technical University of Athens in 1984, prior to the actual construction of the trireme Olympias. And the lines, even though it doesn't show up very clearly here, are the ones that we used for the model here at Stevens. And there's an example of the model in the testing tank in Athens. This is the automated milling machine that is over in the Davidson Laboratory, actually over, I think it's that direction, and it's actually a little bit, actually almost in downtown Hoboken. That's the model basin itself, and here's the model with the cutwater bow. And you can see some of the students and instructors arrayed around the tank. So good facility. It was perfect for this kind of experiment. What I'd like to do is show you first the lines drawings. This makes it a little bit clearer of what we meant by a merchant bow versus the cutwater bow. So we created the model, cut off the nose. What you see in blue would be something more representative of what a typical merchant vessel of the era might look like. Speculative, but probably reasonably representative. This is the cutwater that, after looking at the iconography, the archaeological evidence, our professors here, Bill and John, decided would probably be the closest to what the ancient cutwaters prior to the ram might have looked like. And what you'll see is the blue is the merchant ship bow and how that compares with the cutwater. So the idea, as I said, was put both models in the tank, compare the results. Well, John, I think you want to see if you can pull this one up. This is the merchant ship bow, and it doesn't play on here, so John's going to pull up a file that does. And you'll see that it was tested at a number of different speeds, but I want to show you the one that was tested at 9 knots. And I'm probably going to ask you to play it several times because it goes by pretty quick. So you can see.
Do it again?
Yeah, let's do it like 3 times. So have a look at the wave buildup and the wave starting to actually not just form, but break over the bow.
I'd just like to add, the test had to be stopped because the ship was flooding.
Yes. So those waves were not just being created and generated forward, but it was pouring over the bow into the model itself. Breaking waves in a model are generally frowned upon. At least when I was a student, we tended not to enjoy that. So this is, this is at 10 knots, not 9 knots.
Yeah.
So this model, they stopped the experiment. If you look at the tests at slightly lower speeds, you still see considerable bow waves. And I'll talk about wave making as resistance a little bit later. Let's go to the cutwater.
Okay.
This is the cutwater 11 knots, I think.
You want the 11 knot one?
Yes.
Go for it. Yeah.
Move the pointer, John. John.
Oh, yeah.
Pointer out. Not that far out. I'll get it.
Do it again.
Okay, at this point you can
Sorry.
Okay, you can see that it is generating a wave. That wave is far smoother and flows very gently around the hull. And this is at a much higher speed, 11 knots. So that gives you visually something that we saw in the physical representation.
Okay.
You guys want to see it one more time?
Yes.
Yes, let's just keep playing it. Go ahead. This is the coolest result, by the way, no question for me. When I first saw this video, I said, I had the aha moment. The aha moment meaning, my God, it may be that ship designers 2,000 years ago knew a lot more than I do about what makes a good ship. Now, I'm going to be very careful about several things. Number one, we have no way of knowing whether this was why the bows on these ancient iconographic representations and the archaeological bows were built. We don't know that. This is an attempt to come up with something that is a plausible conclusion. And let me show you. So if you can go to the next slide. Oh, I got the, I'm sorry. So there's the cutwater bow. And I'll walk you through the technical part. It doesn't come out as clear as I wanted. Let me show you a couple things here. This is called a speed power curve. Among naval architects, this is kind of our bread and butter. What this is showing is the horsepower required to push a hull at different speeds. The red curve is the speed power curve for the merchant bow ship. And so you understand, the higher up that curve, the worse you are. You want to be as low as possible. In other words, lower power per speed. The blue curve is the cutwater bow that's been tested here, and the green curve, which doesn't come out as nearly as well as I'd hoped, is the scaled result from the Athens model basin testing back in 1984. And this is what it's showing you. To reach a speed of about 8 knots, this merchant ship bowed hull requires about 30 horsepower. For that same horsepower, whether generated by wind or by rowing, and we are not taking into account a lot of other things that would go into a real full-scale model like the resistance of the Orders and so on. This is what's called a naked hull, bare hull model. For that same power, the ship with the cutwater bow could go closer to 9 knots. And 1 knot difference doesn't seem like a lot, except when you're actually trying to cover long distances while rowing. Getting there, 1 mile an hour faster is a lot better. And that green curve, which is a little hard to see, which is the model testing done on the trireme, shows that there's very little or no penalty going from this cutwater to the ram, which has, and both Bill and John will be talking about ramming a little bit later. The rams look different than the cutwater. They're heavier, they have large fins, but in terms of hydrodynamic resistance, there's very little penalty obvious from here. Now, I have to be careful also, we're comparing 2 different models done at 2 different times in 2 different tanks. Perhaps there are some minor differences, but in the bigger picture, very little penalty is paid. So again, to support the idea that the cutwater provided some kind of benefit that was recognized very early on in these Mediterranean vessels that enabled ships, whether under oar or whether under sail, to travel faster, using the same power, that is a plausible theory. So that's what we were trying to demonstrate just from the scientific and historical end of this project, apart from the pedagogical benefits. I think this shows that there's definitely some meat there to be further explored. So we know that the ram bow, as I said, Bill and John will be talking about that later, was the principal weapon in Mediterranean navies long into the Common Era, and only started to fade from importance around the time when cannon became the principal weapon, sailing ships became the principal kind of warship. There was a transition period where the underwater ram was eventually replaced with above water equivalents, but for our purposes, let's look at why the ram became the principal weapon in the 19th century. This is how ships would fight between the era of the rowed galley and the iron steamship. This is the Battle of the Chesapeake Capes. This is the battle that created the United States of America, or at least allowed it to exist, between the French and the British, and the, spoiler alert, the French won, which allowed Yorktown to happen. But this is how battles were fought. You had large ships of the line. A ship of the line was a very substantial sailing warship. It could displace 3,000 tons. It could carry between 50 and 120 cannon. These were typically carrying about 74 cannon. And they pounded it out. The cannon were firing against masts, hulls, creating damage. They didn't sink each other very often, but they created an awful lot of damage. And what you see here is a fairly typical arrangement of lines of ships. That's why they're called ships of the line. Sometimes over a mile long, duking it out. One fleet wins. That's how battles were fought. So firepower in terms of number of cannon was critical. Along comes steam. Along comes iron. The nature of battle changes, and there's a problem with both. This is a 74-gun ship of the line, circa 1812, our war of 1812. 3,000 tons, 74 guns, a lot of firepower. Just 30 years later, steam comes along, and the problem with steam is it takes a lot of room to put in engines, stacks. So your 3,000-ton ship now has 20 guns. So the firepower is limited, and that's the first problem with steam warships. You also have the problem of protection. Wood, compared with iron, is not easy, but certainly more susceptible to devastating damage. This is the the CSS Virginia versus Monitor, and they were firing at point-blank range. You can see the extent of damage that was caused on Monitor. The iron protection that was afforded meant that for many, many, many years, projectiles simply did not have the penetrating power that against iron armor that shot had against wood. So the two problems, lack of firepower, and the firepower that you did have really didn't penetrate the enemy vessel, led to the idea that you could take these iron warships and make them into rams. The French Navy was the first one to really push this, but every single navy around the world had, in one way or another, for for much of the 19th century, the ram. This is the first purpose-built ramming ship, the Solferino. The fellow who was pushing this, a young lieutenant, Labrousse, said, as in Rome, the ram will reestablish equilibrium in favor of courage and diminish superiority found on greater numbers. It was a very theoretical argument for why the ram would be specifically useful for the French tactical thinking, which was based on spirit and elan and going into the enemy full bore. But here's the point. Solferino was equipped with a number of cannon, but 5,000, 6,000, 8,000 tons of iron propelled at 10, 12 knots with that ram in the front. That's what's going to do the damage. That was the idea. The guns were there to disable some of the ability of the enemy to maneuver, but the coup de grace, that was the ram. Now that was the theory. And it was used in the 19th century from time to time. That same battle that I just pointed to, the Monitor and the Virginia, was preceded by the Virginia ramming and sinking Cumberland. Cumberland was a wooden ship at the Battle of Hampton Roads. Most famous was in 1866, a few years later, during the Wars of Independence for Italy. The Ferdinand Max rammed and sunk the Re d'Italia. Down in South America, Huascar, during the Chilean, Peru-Chilean War, rammed and sank the Esmeralda. So the ram was seen as the primary weapon. It was generally used when one ship was almost disabled, as it turned out. I very specifically avoided the term ramming speed, you noticed, when we were talking about triremes. It turns out that ramming is more a question of maneuver than it is of speed. A couple of reasons that were true in the days of the trireme and also true in the days of the ironclad. First, if you are going too fast, that ram can become, actually the whole ship can become embedded and stuck in the enemy's vessel, and you don't want that. More importantly, it's very hard to aim and hit something maneuvering at high speed. So most of the ramming that was done in these scenarios were done at reasonably lower speeds, between 5 and 10 knots. As I understand it, this is also probably true for many of the trireme actions. Ramming was intended to disable and sink the enemy that had already been disabled. Great theory, but apart from these three battles, there's not a lot of other evidence of the ram being effectively used in battle, even though it played very heavily in the naval literature of the time, even in the fiction of the time. If anybody here is a fan of H.G. Wells' War of the Worlds, there's a famous scene where I think it's called a ram, defeats one of the Martians. But when you read the text carefully, it doesn't destroy the Martian machine with its guns, it rams it. So the idea of ramming was pervasive throughout the 19th century. The reality was a lot different. It was more often deadly in accident than it was in battle. These are just two of many, many examples. 1875 and 1893, where British warships on maneuver accidentally rammed and sank each other. And this happened all the way through to 1914. The most, to my way of looking at it, important ramming event occurred in 1911, and that was the Hawk versus the Olympic. Now this may not look like it should have been important because there's the Hawk. It's a cruiser with a ram bow, and it collides with RMS Olympic in 1911 in Southampton Harbor. And you can see the bow portion, the top of it, creates that hole here. Underwater, there's the hole that was created in Olympic. Olympic limped back into port and they repaired the damage. Notice who the master of Olympic was in 1911, Edward Smith. Edward Smith was so convinced that the design of the ships made them invincible, that Olympic and Titanic, well, being the same model, and I'm going to read this quote. This was from the Washington Times, April 16th, just a few days after the report of the sinking became news. And the word that was often used after the fact was Titanic is unsinkable. And a lot of the people who looked at this said, oh, that word was only applied after the event. Here's what Captain Smith said prior. He said, regarding the Olympic is unsinkable, and the Titanic will be the same when she is put in commission. So here we have Captain Smith thinking, as he's commanding Titanic for the first time, that he's got the same kind of unsinkable vessel as Olympic was. And did this actually affect his decisions on whether to go at full speed through an ice field? We simply don't know. But we do know that he certainly regarded his ship as unsinkable. And we know that he regarded it long before the ship was put into commission. Unsinkable was a term, and let me be very clear about this, that was in his mind at least before the ship put to sea, not simply an artifact that the press created afterwards. And that ram bow was the reason that he thought that. Let's talk about the bulbous bow today. Many of you, if you ever have been on a cruise, have had a chance to look at the bows of the ship, and you're wondering, why is that bulb there? In the 1950s and 1960s, this gentleman, Takao Inoue, came up with the idea and tested it that a bulb, something that's projecting forward of the bow of the ship, can do something, can create something called an interference wave. In other words, and it's a little hard to see, but if you look at the top wave, that's the wave that is normally caused by the bow of the ship moving through the water. Wave making is a major part of the resistance of a ship. The bulb, just as a bulb underwater moving at the same rate would create another kind of wave, and that's the bottom wave, that would be somewhat out of sync with the ship's wave. And the combination of the two, that heavy line in between, is that lower, smaller wave, and that lower, smaller wave means less wave-making resistance. So bulbs actually create an interfering wave that, as you can see from these two full-scale tests, greatly decrease the wave-making, therefore the resistance. That's more or less what appears to be happening with the cutwater. We have not done any in-depth scientific investigation, but that's the kind of wave-making appears to be the critical issue here, and this helps to explain it. There's his first model. So starting from the 1960s, we were building ships with the bulb, and this is what we see today. Cruise ships have bulbs, cargo ships have bulbs, yachts have bulbs, freighters of every ilk are built with bulbs because they provide a hydrodynamic benefit that we've only started to realize as of about 40 years ago. So that's what we see today, but I want to leave you with this. Yes, we have a bulbous bow today because it is a scientific and engineering artifact that improves our ability to under power, but the bulb is still a weapon. Here's two examples. The DD-968 Radford was struck by a container ship in 1998. You can see the hole left in the side. And back in 1986, at the time, the Soviet passenger ship Nakhimov was holed by a bulker with a bulbous bow, 423 deaths. So even though the bulbous bow is built for completely different purposes, it can still act as a ram today. It's still a weapon. So we've come full circle, And what I'd like to do now is go ahead and open up the floor for questions.
Pick up the lights too.
Yeah.
Larry, can you just comment, speculate, I should say, on how you see the relationship between do you think it's identical, the interference that goes on with the bulb and the cut water, or do you suspect differences in the interference patterns?
Okay, so this is being recorded, so I'll repeat the question. The question is whether the bulb that we saw, I'll move back a couple, whether this pattern is similar to what we're seeing in the cut water. I think that the science is the same, but we're seeing somewhat different effects. The cut water is number one, is operating fairly close to the surface. What we have designed there is a little bit longer. I think what we're seeing is not just simply an interfering wave, but a series of interfering wave patterns that together generate a different wave profile than you would get from the merchant bow. So I think the science is fairly comparable, but the exact nature is something I'm looking at you, Stevens, investigate a little bit further to see whether this is a somewhat novel phenomenon. But it certainly, to my way of viewing it, is all about how that cut water is generating waves in front of and interfering with the hull waves. Does that answer your question?
Any other questions?
Sir?
The modern merchant hull bulb, you say it's an interference thing, it is actually, I believe, designed to be optimum at some particular cruising speed.
They are generally optimized for specific sets of speeds,
Right.
and the better we are at it, the more wide range, the wider range those speeds can be.
Could be.
So there's usually like some kind of plateau.
I'm going back, in the 1960s and early 70s, tankers began to get outfitted these for optimum speed.
That's correct.
At a particular high speed, and then when the price of oil went up, the speeds went down, and some of the advantage went away.
So the comment was back in the 60s, they were optimized for the top speed of these vessels, and then as the price of oil went up, the actual operating speed was lowered quite a bit, and that's absolutely correct. So they started to optimize bulbs for different speeds. You might be interested to know that today, although this information is about a year old now because the price of oil has just taken a tumble, when oil prices were very high, we were looking at operating ships which were originally designed for 18 and 20 knots down to operate down at 12 knots, and in some cases down to 5 and 6 knots. Speed and power are not directly related. Power is the cube, goes up as the cube of the speed. So if you're going half as fast, you're going using only 1/8 of the power. So today we're actually looking at super slow ships. Odd for a naval architect to be discussing how to design a ship to go really, really, really slow, but that's one of the things that we are investigating today. So you are absolutely correct. I know there wasn't a question, but you are absolutely correct. And thank you for the riff. So other questions? So you first and then over there.
I'm just curious, the trireme and these weapons. I take it that instead of speed, as you mentioned, they're meant to rip, right? I mean, it seems you have to get up close, and it's sort of, is it intended to rip the side of the ship instead of like you said?
Is that something I can ask John and Bill to talk about when they are talking about theirs, or do you want me to?
Okay.
Yeah.
Well, first of all, they know so much more. I use the word cube. Take a few powers higher, and that's their level of knowledge. So I'm gonna let them answer. There was a question over here. Yes.
With the original cut water that was on the ships, you said you're not sure if it's definitely for the wave making effects and that it was too light to be a weapon, is there any other theories out there why it might be? If it's just like possibly just an aesthetic thing, or?
Again, actually, this would be a good question. Could I ask John or Bill or both to weigh in?
Hi, I'm Bill Murray. You have to think of it from a historical perspective. You have a funny projection that appears on a warship, on a ship, and it continues for 1,000 years. Something like that would be abandoned immediately if it had a deleterious effect. I think various theories that I've heard is that it serves as a nice boarding plank if you want to get from the bow of a vessel to the beach and you go up bow first. We have some images that show crewmen squatting down on it, and so it's been interpreted as a latrine. It probably had multiple purposes in reality, but the fact that it is so persistent in these designs, and the fact I think most naval historians long ago concluded that it was for hydrodynamic reasons. And so what I find so interesting about the Stevens tests is the fact that it is now demonstrated that it makes sense hydrodynamically. And I'll try to say in my paper about why speed does matter, and certainly John Hale will talk about why speed does matter with these oared warships. It's a critical element in the ship being used as a weapon. So I don't think there's any doubt about it.
Thank you.
John Hale, University of Louisville. There is a little doubt in that there are two brands of ancient ship. Round ships, which are powered by sail and used for moving merchandise. Long ships, powered by oar, by humans. Only the long ships use the prow projection. If it's got a general benefit, you'd think that they'd be experimenting with the sailing ships, and they don't. So.
I was wondering, we'll wait later for you guys speak, but it looks like when you look at the power profiles, at the lower speeds it doesn't much matter. And it's only at the higher speeds that these two bows make the difference. So when a sailing ship isn't going very fast, you wouldn't think a color would help it at all.
And that's absolutely correct. So the comment was, it's not really helping an awful lot at the lower speeds, and that's absolutely correct. So very quickly, at the lower speeds, there's two primary components of resistance for ships. That's frictional resistance, the rubbing of the water against the body of the hull, and the second is wave making, which is drawing energy off the hull to create waves. That's the way we think about it today. At these lower regimes, 2, 3, 4 knots, you see very little difference in the two because most of the resistance is due to the friction, and that cutwater does not benefit frictional resistance, actually makes it a tiny bit worse. So in the typical speed regimes that most of these merchant ships were operating, under sail might have been anywhere from 2 to 4 knots, sometimes lower. There is not a lot of hydrodynamic benefit. Plus, if you look at the way these round ships were built, I can imagine that it's a little hard to develop a bow that would be able to have a cutwater well integrated into that fairly broad, bluff body, which you need to carry heavy cargo. I mean, keep in mind, they were carrying cargoes weighing tons, tens of tons, hundreds of tons. You need pretty sturdy ships to do that. These trireme type vessels were fairly light, fairly narrow. In terms of the load, they were carrying people. So it was a much different design problem. Was that a question, or you want to make a comment?
I just want to say that another thing that you would have to do would be a tank test is one thing. Instituting waves is another thing. So I think what you'd have to do would be to get these ships out there and then throw in 1 foot waves, 2 foot waves, 3 foot waves, different wavelengths, and see what that does as well with the hot water on it.
Thank you, that's a good point. This is a calm water test. This does not show what things look like in the Mediterranean in anything that look like a wind-generated wave system. So even today, we worry about how to model ships in real sea conditions as opposed to just in calm tank conditions. Very good point, thank you. Did I see a question there? Sir?
Could it be just fashion? A long ship ending in a projected bow?
So the question was it just something
Just
aesthetic?
fashionable. Like, the stern doesn't make much sense of those ships. It doesn't function. It's just a fashionable
An
thing.
ornament.
It's just something that they like to do.
So I thought Bill kind of talked a little bit about that. If it served anything that took away from the operation of the ship, it probably would have disappeared. Bill, I don't know if fashion is deleterious or beneficial.
There's one other factor to consider.
And I'll try to mention it in my talk, is that the waterline whales come into the cutwater in a way that mimics exactly what happens to the wood network that is inside a functional ram. And so what you see is that the forces of the ramming collision are translated back to the bottom timbers of the ship's hull. And so I don't think it's any coincidence that the cutwater develops into a ram eventually, because the timbers are already in precisely the correct position that you want them to be in when you start exerting collision forces to the bow. So that's another thing to keep in mind.
So again, we are speculating. As far as I'm aware, no one left anything that said we did this because of this reason. And I can tell you, as a historian of naval architecture, of ships being designed all the way through till 20 minutes ago, it is sometimes surprising how blank the record is of why design decisions are made. I designed frigates, aircraft carriers, cruisers, destroyers, you name it. And we did not, as practicing naval architects, always record exactly why we did what we did. That tacit knowledge, that knowledge in the fingertips, and I'm sure the IEEE Center can talk to this in their history, is probably the longest or hardest problem to solve, getting people to explain why they did what they did. And a lot of times what we have to do is ferret out meaning from the artifacts, from the few surviving papers, to understand what happened. And this is true in computers, this is true in telephones, this is true in triremes. Did this answer your question? It was over here someplace. Okay, there's a question here.
I'm Sheldon Hockheiser from the IEEE History Center, and partial answer to your question of the why is that's why historians do oral history.
Yes.
That's exactly what you can get out of oral history that you are not likely to find in either the written record or the artifact record.
So oral histories are the key, and having been a proponent for 20 years or more of oral histories in naval architecture, I fully agree. Notice I said proponent and not successful proponent.
Yeah.
Because as it turns out, getting people to fund oral histories of engineering can sometimes, quite often in fact, be one of the longest poles in the tent. By the way, just quickly, how are we doing on time?
Well, we got lots of time.
So I got lots of time? Oh, then I can just, sorry, go ahead.
Oh, no, let me just, well, while naval architecture is outside of IEEE's fields of interest, by
Should
and
it
large.
be?
What?
Sorry, go ahead.
Well, that's another question. IEEE, we have over 600 oral histories posted on our website, because in a whole variety of things within IEEE fields, going back into the late 60s, just for that reason. I can't address why naval architects have been reluctant to fund such work, but That's the answer to the question.
Yeah, so IEEE, and I visited their site, and they do have a fantastic array of oral histories. They really are wonderful. All I can do is commend you to go to the website.
I just want to amplify what he said, if you're studying history of engineering, about the printed papers, patents, don't tell you what's between the lines. And very often engineers are tweaking things constantly, and that's why companies have trade secrets, because what they put into a design is not on the paper necessarily, it's what's in their heads and how they tweaked it. So that's why moving people from one place to another is the best way to get transfer of technology, not moving the papers and the.
So, yeah, this history of transfer of technology is interesting. We don't really go into it in here, but there's a lot of wonderful work done on technology transfer, both at the national level, at the industrial level, and at the international level. And as a plug for people involved in maritime business, the oldest examples, my argument is, of technology transfer are probably in the maritime field, where you see examples between nation states and between peoples in the Mediterranean and in Asia, etc., where practices find their way from one place to another. And there's a wonderful history there. Other questions? I think one more question, and then we can be done.
Yeah.
Okay, sir.
You said that bulbous bows are relatively new, and that they're seeing them pierce other ships, just like the weapons in the past. Do you see them now taking new action to change the way they build ships with bulbous bows, like maybe move the collision bulkhead forward more so that you're not piercing as far into other ships?
So the question is, the bulbous bow is a weapon. What are we doing about it? And there's actually a lot of studies that have been going on for a long, long time. I'm personally familiar with several. I didn't put them up simply because this floor is slippery. It's not just me.
Oh, it is. Yeah, it is.
Yeah.
But I'll
Some of the studies that have been going on include making the bulb itself collapsible, so that if it does impinge on a surface, it doesn't have any penetrating power. That's being studied. Another line of study is to build ships that have more collision-resistant structures. In some papers that I've done, I'm not showing them here, I show examples of collision tests on the French aircraft carrier Charles de Gaulle, which was specifically designed so that a bulb does not penetrate the shell of the ship that surrounds the nuclear reactor. There's been studies for riverine and non-ocean going ships, which are more susceptible to collisions. Where do collisions occur? When there's lots of ships around. Where does that happen? Rivers, harbors, etc. Generally not on the open ocean. So there's a lot of, the short answer is, there's a lot of study going on about that. It's recognized as a problem, but keep in mind, shipbuilding, unlike automobiles, automobile safety can be dictated at the national level. You almost invariably run up against all kinds of political difficulties trying to instate safety laws that operate at the national level. They have to be done internationally. Ships operate internationally. Ships are bought and sold and owned internationally. International Maritime Organization is the primary vessel, as it were, to coordinate those activities. And it's probably going to take some time. So yes, it's on the radar. It may not be as close in and high stakes as we'd like it to be, but I do see a path forward.